is a reflection followed by a, oh shoot, I did it backwards here.
Oh.
We're gonna glide first, so it'll be a translation. Sorry.
First.
I'm just like not even together here. Translation. Man, I'm just gonna start over.
Oh, that's cool.
Paper. A translation followed by a
tree.
Reflection. That was embarrassing. Couldn't even write the words correctly.
I forgive you. I don't.
Listed as a diagram here is a glide reflection. We can tell where it's been going for two things. One, I drew arrows in, which you normally won't have. More importantly, we can look at the diagram and see the notation. Our original, this is clearly original because there's no prime notation. Here is single prime, and some of them may not be super clear.
Whoa.
If you have performed a second translation, or second transformation, excuse me, and there's a second image, we'll use 2 primes to note that. And if it's not entirely clear on your copied piece of paper, you can draw them in. But this would be like a double prime, C double prime, B double prime. Again, you could do a triple prime or a 4th prime or however many you need to denote, folks, where the transformations are going. Part of your homework tonight, I'm going to give you a graph that's got at least two transformations on it, meaning 3 objects, and you're going to have to decide what's been going on. So to do that, pick out the notation. The number of primes will tell you in what order the transformations have occurred. Okay? Let's list what the transformations were, though, for this. So first of all, what was the first transformation? And more importantly, since we can qualitatively list it, let's also quantitatively list it. So let's also give us the rule for each of these. Or for a translation, certainly, what's the rule for this translation? Negative xy. So when we go to a to a prime, it would be what, -3, 2.
No.
It would be like -12, 0.
In vector form, sure. As a vector transformation or translation, it could be -12, 0, or Steve, what were you saying?
X minus 12, y.
Steve or Steven, no.
We could call him Steve.
No, we're not calling it Steven.
Let's call him Ryan.
As a vector. Okay, once we've got this translation, folks, once we have the translation, what's our next transformation going on? Over what line?
X over the X line of symmetry. Axis.
So the reflection over the x-axis, or if you want to list it by its equation, it would be the line y equals 0. So when I ask you what transformations have gone on, I want to know more specifics than just a translation and a reflection. Sure, you can do that, but so can a 7th grader. You guys are now in essentially accelerated geometry. You can handle giving me a rule and telling me what line it's being reflected over. In general, you don't need to necessarily do just a glide reflection. You could do a composition of any of these transformations in general. A composition is simply just performing more than one transformation on an object. In general, you could just compose any two of these transformations. So you just perform more than one. So do one, then another. Okay. A glide reflection, folks, please stop interrupting me. A glide reflection is a special kind of composition. It's a translation, then a reflection. If you perform a composition or just pick any other two and combine them, or if you do reflection then translation, or any two or three or however many you want, in general it's called a composition. So a bunch of your homework tonight is going to be to identify, well, what has been performed. So for example, in this diagram, first of all, what's the first transformation that's gone on?
Reflection of the Y.
First we have a reflection over the y-axis. We can tell that's the first one because R and S with no primes is clearly our pre-image. Our first image goes to R prime S prime, which that looks to me like a reflection, for sure. But what's our second transformation? Oh, sorry. I'm sorry. This is a rotation by how many degrees? Are you sure it's 90 and not 270?
Yeah, because I'm sorry, going worse.
For origin. About or around. About means around.
I almost spelled potato instead of rotation. Just put it out there.
Two ways. Last hour, someone asked, how do I know it's exactly 90 degrees? I had two answers for you. First of all, you could go in the context of this course. And yesterday we said we're going to, if we're talking about explicit rules, we're going to be talking about exactly either 90, 180, or 270 in the context of this course. Secondly, you could have also known this exactly 90 by checking the coordinates and seeing that R prime to R double prime is flipped and changed the sign of B, which is the exact coordinate rule of a 90-degree rotation. So you could have looked at the coordinates and found that it follows the coordinate rule for a 90-degree rotation. Would have been another way to check. Okay. Let's do a couple examples. It's on the back side.
Wait.
Back on the flip side.
There's a couple examples on the back side. I'll do the first one with you, and you'll do the second two. Sketch the image of A, which is 2, negative 4, after the described composition. So what I'm going to do is I'm going to go through, I'm going to figure out what A is. I'm going to list the A is 2, negative 4. I'm going to find an intermediate image, between image after the first transformation. And then I'm going to find my final image, which in this case, since there's 2, and I'm going to change my note sheet to say A double prime. I'm going to do 2. So you could try to do this graphically. Unfortunately, there's not enough graph paper to graph the two prior images. So I'm going to perform the first. So translation, xy goes to x plus 2y. 4, negative 4. After I've done that, now I'm going to reflect it over the x-axis. Then what does do we remember what the coordinate rule is for a reflection? Reflection over the x-axis. Make the second term negative, or change the sign of the second term, the opposite of. So the opposite of negative 4 is positive 4. So A double prime should be 4, 4. And that's right here. Okay. If you wanted, you could graph each of the two pre-images, the pre-image and the intermediate image. Unfortunately, you'll discover that you'd have to graph somewhere down here. I didn't give you enough graph paper below to do that. You could if you wanted. Okay. In fact, I would recommend doing that for number 2 because you're reflecting over a line we don't have a coordinate rule for, y equals 2. So I certainly am going to want a graph where a prime is before I try to get to a double prime. Okay. Let's see. Let's on your own. Let's finish. Let's do number 2, and let's find the coordinates down here for the triangle that's listed. Pre-image, recall, would be our original. First image, and the second image. All right, it seems for number 2 we should have, let's see, A, the original is actually 2, -4. After the transformation, it's -2, -1, which is here. Reflecting over the line, y equals 2 would help to draw in that line, which is a horizontal line. So now we're what? If this was 3 below, so it should be 3 above, which is at 2, -2, 5. Let's see. I have faith that you could correctly write down the pre-image coordinates, folks. Let's do by hand raising method here. What's A prime, the first coordinate? Page. F21. Greg, B prime. Folks, you need to stop talking, please. C prime. Okay. A double prime. Sarah. B double prime. Gregor's again.
3 - 3.
C double prime. Kate.
1 1.
1 1. So our coordinate should look like here: C double prime. B is 3, -3, and A is what? -2, -1. Is our triangle after this composition. Okay. We need to add one thing to the notes, which is not printed, but we have plenty of space below. There's one theorem from the book that I did not type on the notes that it's going to be pretty necessary for a couple homework problems. This theorem is what's called the double, well, I'm calling it the double reflection theorem. And it deals with finding the angle measure, finding a relationship between a rotation versus reflecting a point, say, over 2 different lines. Okay, this is pretty important considering it's not typed on the notes. So this, it says that if you have 2 lines that intersect, I'll call one L and one M, and they intersect at some angle measure. We'll call it X degrees. Probably not the most appropriate name, but whatever. Okay. And let's say we want to reflect a point over each of those 2 lines. So let's say we want to take point A and reflect it over line M. And then we want to then further compose that with a reflection over line L. So we're going to reflect this single point twice, is what the theorem is saying. This is what you're trying to do. If I say do 2 reflections in a row, once over line M, once over line L. Okay? The theorem says the following. It says that if a point is reflected reflected twice over 2 intersecting lines, then the resulting point, or resulting image, is the same as if the point had been rotated by a certain number of degrees. Does anyone want to take a stab at to what the rotation is going to actually be, the exact number of degrees it's going to end up being? Yes? Not 90. Not, well, it could be 90, but not necessarily 90.
X.
Well, not X.
2x.
Because we're going to, if we wanted to not quite X.
It would be 180 minus X.
180 minus X? No.
360 minus X?
360 minus X? No, it doesn't look like, I don't think so. I think someone kind of said it, I think. It's 2X. So if you wanted to do two reflections, one after another, over these two lines, you could have instead just figured out the angle between them and just rotated by twice that.
Oh,
Would
so
do
that
two
makes sense.
reflections.
Like, you have like a normal like